Hey everyone, I'm Rowan, and today I'm going to discuss my supervised learning project as part of the AI and deep learning models for actuarial application course. In this presentation, I'll outline the deep learning supervised learning problem which I have chosen. Then data collection will be discussed, which includes sourcing, pre-processing, and core findings from the explanatory data analysis. Afterwards, the architecture and findings of the benchmark and both deep learning models will be explained, and we will end with discussing the preliminary results. Starting with the problem statement, the objective of my project is to predict whether a publicly listed company is solvent or bankrupt, based on the company's key financial indicators, the type of company, and the environment in which the company operates. This problem will help make investors make informed decisions, saving financial resources. Moving on to data collection, this data set contains 78,682 observations from 8,262 American public companies listed on either the New York Stock Exchange or NASDAQ. Observations span from 1999 to 2018, although only some companies are recorded across the entire period. A lot of companies only have observations for a certain selection of years. All information sourced is publicly available financial data released by companies and was compiled on GitHub. When pre-processing the data, I first checked for missing values and addressed them by removing their rows. Then all columns were renamed to descriptive names, which are stated in the data dictionary. The status label variable was mapped to a binary numerical format and stored a new variable status. Finally, I removed the variable total current liabilities due to its one-to-one correlation with total liabilities. In the EDA, it was found that 6.6% of the variable status was equal to 1, which means that there is a significant imbalance in the target variable. Moreover, there is strong correlation between some of the predictor variables as demonstrated in the correlation matrix, but status has quite a low correlation with the predictor variables. The benchmark model that I'm using is a simple logistic regression. It was built on sklearn, and the continuous data was standardized, while the categorical features were encoded. After it was fitted on the training set and ran against the validation and test set, the following results were produced. Although the model is very good at predicting the not bankrupt cases, it is bad when it comes to predicting bankrupt cases, as proven by the low true positive number in the confusion matrix and the 0% recall. The first deep learning model that I've used is a relatively simple feed-forward neural network. This was built using Keras Sequential API. The input layer consisted of 20 features, and the continuous variables were kept the same. Only the categorical variables were encoded. There are 3 hidden dense layers using the ReLU activation function with 100, 50, and 25 neurons respectively. The output layer uses a sigmoid function with a binary output. The model had a binary cross entropy loss function, and it ran for 106 epochs before early stopping kicked in. Had a validation accuracy of 94.12% and more true positives but less true positives as shown here in the confusion matrix. The other deep learning model that I've used is a deep and wide neural network. This deep path utilizes the categorical inputs, which are entity embedded and reshaped before being trained with scaled continuous features and ran through the first dense layer with 64 neurons. The wide path uses 18 continuous inputs and sends them straight to the second concatenate layer. Afterwards, the feed-forward neural network is repeated until the output is reached. There are 2 dropout layers that exist in both the first and second dense layers, with 20% of neurons being removed at each layer. Early stopping on this one occurred after 124 epochs, and the validation accuracy was 93.37%. As demonstrated in these 2 graphs, the training accuracy is quite high as the number of epochs progresses. But for the second model, the validation accuracy is more stable due to the presence of dropout compared to the wide variation in the first model. This preliminary results table portrays how both deep learning models perform slightly better at predicting the bankrupt cases, but the trade-off is that it predicts slightly worse prediction for the non-bankrupt case. The accuracy for the 3 models are very close. And with greater adjustment to both neural networks, there is definitely a case for utilizing a deep learning model to solve this type of binary classification problem.